Everybody, everyone can hear the meeting is now being recorded, so we're going to try to go through this and try to talk a little bit about the climate and residential modules in GridLAB-D this morning. If there's any questions, please feel free to ask them in the chat window. I am kind of working this one by myself today, so it's not as maybe not quite as smooth as it normally is. So it may take me a second to see the messages themselves when they pop up, but I will get to them eventually. But what we're really going to try to do is talk about some of the ways that GridLAB-D interacts with some external data, how we do a lot of our load models, and how to move that information in and out and use it, particularly use it in conjunction with load models, in conjunction with the power flow model. So we're going to walk through this. I don't think the material will take too long to cover, so we'll actually at the very end we'll spend quite a bit of time going through some samples, answering questions, digging in more deeply to what others might want to explore on here. But like I said, I think the presentation material is only about 2.5 hours at the most, probably more like 1.5 to 2 hours. So again, feel free to ask me any questions, and we'll go ahead and get started. Is everyone able to hear me okay, or do I need to turn up the volume at all? All right, so what we're going to talk about now is the climate module. So quite obviously, the purpose of the climate data is we want to move all of our weather information into the model so that we can use it for a number of different things. That ranges anywhere from the way that the loads interact with the system, how the generators interact with them. So for example, wind turbines and solar panels, things like lines. We can do dynamic ratings on lines. All those type of things that we may want to affect as a function of different climate or weather parameters. So of course, there's a number of different sources of weather data. We have our typical meteorological yearly data, which is a great data source produced by, well, it was originally produced by NREL, and now there's a number of different number of different agencies that use it across the world for converting data into basically what are very average annual data sets. But there's also others. For example, you can go and find things like NOAA weather records. You can go and find weather stations. There's a number of different things. Everyone's quite aware. Weather data is becoming pretty prominent and easy to find. But of course, each of those sources has issues. So I'll kind of go through some of what we use typically and some of the things that we've seen with some of the data sources, and just kind of give you a few experiences that we've used with them. So TMY data is actually supplied with GridLAB-D. So when you download the executable, you install it, TMY data for the United States comes along with it. This is roughly about 300 cities across the United States. They represent very, very average data for those cities. Literally what they do is they go through and they have 12 months or they have 20 to 30 years of data. For each month, they pick out the most average month, and that becomes that month's data set, and then stitch them all together to form a yearly or annual data set that represents roughly the climate of that city. This does lead to some problems. So for example, because they are stitching together certain months, you can see some discontinuities. So for example, from the end of March to the beginning of April, you may see the temperature jump by 30 degrees because in a 1-hour period, because it was 2 data sets stitched together. Again, these are typically designed for climate studies, not necessarily weather studies. So there are some issues with those, just to be aware of. Note, data files are large. I should probably change that. That was the case 8-9 years ago when this model was being put together. Now these aren't that bad. They're a few megabytes apiece. But they have things like latitude, longitude, city, state, all those type of things. All those are used to correct for different solar angles so that you can do things like depending on where, which latitude you're sitting at, you will get a different amount of normal direct solar radiation at different times of the day. So it does corrections for which latitude you're at. Things like temperature, humidity, solar, and wind. These all come in from the TMY2 data as hourly data. But of course, a lot of things that we want to do in GridLAB-D are not hourly. They're actually much shorter time scales or even much longer time scales than hourly. But specifically for the shorter time scales, we've developed a number of interpolators, quadratic and linear, that basically just kind of smooth out that data to take out some of these discontinuities that I was talking about. There's a note here about the fact that TMY data does not drive simulation. And what that means is if you don't have a recorder and you don't have a start and stop time in your clock, the weather files will not make this recording move forward. So you will need to actually still add a recorder in there. So in the SourceForge repository, there is a folder that's got all of the TMY data stored in it. Like I said, basically most of the large U.S. cities are supported, about 300 of them. When you go to this data source, they're zipped in there by state and then cities. So for example, if you went to California, you would find that there's roughly, I think, about 18 cities in there that you can download the data for. And basically, like any of the other player inputs or other input files that you would use with GridLAB-D, basically put this in your local executable file, or if you have other folders that are mapped for GridLAB to access, then you just drop it in there and it will find it and use it. Now there's often you don't want to use climate data. TMY2 data is somewhat hard to work with, not as hard as the first TMY was, but it can be a little bit awkward when you start looking at the format of it. So we wanted to create a way that basically you could bring in any data that you wanted. So this is what CSV Reader supports. CSV Reader is basically, I have my own weather data, I'm just going to stream it in, and I'm just going to put that file in, put that in there and put it in time and date stamps, and that's my weather. So basically any variable that's supported by the TMY reader or the climate, we also support inside the CSV reader, so that's things like temperature, wind speed, humidity, solar, incidents, things like that. You basically specify what's the timestamp, you specify what the value is that you want for each of those, and it pulls it in and basically just feeds it out to the rest of the simulation. In one particular thing inside the CSV reader is things like unit conversions, interpolations, all these kind of extra things. These aren't supported. It's basically assuming that if you need 5-second data coming in from your CSV reader, then you're going to need to put in 5-second data and do the interpolation offline. And I'll show examples of how to use both of these here in just a moment. So an example of how the CSV reader format looks, this is the actual input file. It's got a bit of an odd format, especially for the time date stamp. We're actually fixing that for version 2.3 that's coming out here in January. But basically what it looks like is this first column here ends up being your time and date stamp. It reads as month, day, hour, minute, second, reading left to right. So this is January 1st, 4 a.m. Because there's nothing there, it just assumes minutes are 0 and seconds are 0. And because of the two column headers, temperature and humidity, this first column being temperature says that basically at 4 a.m. the temperature will be 50 degrees and the humidity will be 5%. At 8 a.m. the temperature will be 62, humidity is 0.16. So basically it's just a way to feed this information directly into the climate model. Couple caveats on there. There are a couple small bugs in this reader. It does not support daylight savings time. So if you were to go in there and basically put this reader in there and then set your clock for PST plus daylight savings time, it would not make the adjustments for you. You would actually have to go in there and manually say, at this time, I want this to skip from 2 a.m. to 3 a.m. To handle all the different daylight savings pieces. So here's what's available out of the climate object. There's your kind of basic things: temperature, humidity, solar flux. Notice that this is in 9 different orientations. Basically, what is the cardinal compass points? So you got north, south, east, and west, and then northwest, northeast, southwest, southeast. And then the 9th one is the diffuse radiation. So basically, all the reflected off the clouds and off the buildings and all that type of thing. You have wind speed, wind directions, wind gusts, record temperatures in solar, the ability to do interpolations. One that's not on here is also pressure. So it kind of covers some of the standard climate and weather parameters that everyone's kind of used to. So an example of how to activate one of these, pretty simple. If you're using TMY2 data, it's very easy. One object at the beginning of the file, just object climate, TMY file, name of the TMY file. That's it. It activates everything. CSV file, so if you're using the CSV Reader, now you just have to create 2 different objects, one that activates the CSV Reader and one that then converts that into the climate settings. So once again, fairly simple. Another caveat on these is currently we only support 1 weather file per GLM. So for example, if you wanted to look at, say, 2 feeders that are kind of disparate in geographical locations, you would have to actually simulate those as 2 separate GLMs rather than as a single GLM. That's something that we're going to be fixing for version 3.0, but for now that's a limitation on there. So whenever you would activate one of these climate objects, whether it be a CSV Reader or a TMY2, any of the objects within the model that are capable of accessing and using climate data will basically go in and find this model, and we'll link to it, and we'll pull that information in as it comes and use it. That's really the entirety of the weather pieces and climate. I just wanted to kind of give a brief introduction before we move into some of the load models, just to kind of give you a flavor for what's in there. Are there any questions on the climate model and its uses or anything like that? All right. Well, then we will move on to the residential model. So the residential model, this is a way that we have put together different complex load models so that we can look at things more than kind of the static zip models that most engineers are used to, or even some of the load shape models and things like that. This is kind of our way of going the next step beyond that, and trying to capture a lot of different things, like, say, what's the effects of demand response signals on how consumers interact with their household appliances, and what that effect might be on the power system. So it allows us to do things like, when we want to look at something like, say, the demand response signal that's going to do, say, an HVAC set point adjustment. So we move our set points of the houses, doing basically direct load control. So we shift everybody's house from 75 degrees to 80 degrees. It's pretty easy to predict what that savings is as you move from 75 to 80. You can predict how many houses will be off and how long they'll stay off and things like that. The part that's always been a little bit more difficult to predict is the actual the rebound, which is when you start to recover and move back from 80 to 75 degrees on your cooling set point. The fact that it takes a certain amount of energy to bring you back into that steady state, and how the progression of that change happens. So that was what we're trying to capture with this model. So, in the residential module, we have basically 2 different types of models. One is what we call house E, or just object house, and that E stands for ETP, or equivalent thermal parameter model. And we'll get to that in a little bit in just a minute. But basically, what it is it's a physical model that tries to incorporate things like mass effects and heat flows and air conditioner efficiencies and things like that, and how that directly affects the electrical power system. On the second, we also have what we call appliance models. Some of these are basically what I'll call built-in or external load shapes, so pretty standard models. Or we have what I call physical state-based models, and I'll talk a little bit here in a second about what these differences are. So basically, this is what we incorporate. We have these two models, house, and then we have the appliances. And I'll give you a list of the appliances here in just a second. One note, especially for version 2.2 and earlier users, which this class is designed around, House A, which was the early version of House E, but we still keep it in the code, is what we're calling deprecated. It was based on an ASHRAE standard model that didn't incorporate mass effects, which made it basically not usable for demand response studies. So we moved to this new model, and have gotten this one in here and started validating it, working with it. So a little bit more about the house object. It basically has two main functions. This house object acts, it determines the state and the power consumption of the HVAC system through the ETV model and a number of other things. But effectively, it's just trying to find out, well, what's the HVAC doing? As that's usually your biggest load inside your system. But then it also accumulates the effects of all the other residential appliances. So hot water heater, your computer, whatever it might be that you want to simulate inside of the home. It kind of accumulates those all up into what we call a panel. And that panel is roughly supposed to represent basically like the panel inside your home. So it has 220-volt circuits and one 240-volt circuit. And you attach each of your appliances to those depending on what type of system it is. So your hot water heater, for example, will default to attach to the 240-volt circuit, while say lights will default and attach to the 120-volt circuits. The house actually interacts with the power system by attaching to what's called a triplex meter. I think we briefly discussed that in the last presentation under power flow, but effectively you can think of the triplex meter as it's the meter outside the home, is what it's supposed to represent, but it's also in terms of the code itself, it's the translating device so that so these two different modules can talk to each other, basically so that the residential module, in terms of the house, can talk with the power flow module and can interact and exchange information. Sorry, someone's phone is not muted. Can you make sure and hit mute if you're on the other end of the phone there? As far as, and then of course tying it back to the climate model, it uses climate object to pull in weather data. So in the case of the house model, it uses things like, obviously outside air temperature is pretty obvious, but it also uses humidity, it uses solar flux, so basically how much heat is coming into the house because the sun is shining on the walls. At some point, we're going to add in a function of wind, so that when we have wind, we get actually greater amounts of air exchanges within the house, so you get less efficiencies when the wind is higher, although that piece is not in there yet. So a little bit more description about what we mean by the difference between physical versus implicit models. And this will become a distinction as we move forward, and we'll talk a little bit about why we want to have these different types of models. And particularly when I get to the end, I'll talk a little bit more about sometimes it's not worth doing some of these other more complicated models. And I'll kind of give you some examples about where we draw the line for different types of simulations. So currently in version 2.2, only the HVAC and the hot water heater models are incorporated as what we call physical models. Those physical models are those that we describe as using physical parameters to describe their operation. So effectively, you can say that if you can describe, if the model is described in terms of how you would describe it in your home, i.e., I have a 2,500 square foot home, or I have, UA value 12 insulated walls, then that's what we call a physical model. Typically, these are the ones that are used in what are called thermostatic operations and other types of control methods. So now some of these other pieces in there. So the physical models are these ones that, like I said, are described by effectively the physics of the system. So a good example is the HVAC and the hot water heater. You would describe what is the insulation value of each of these models, what's their surface area, all these different things. The other models that are currently in there, also things like dryer, dishwasher, the range, clothes washer, all these, they are typically represented more by what I'll call a implicit model, which is more of this idea of a load shape. It doesn't actually use a physical description of the system to describe its characteristics. Now, caveat that a little bit because the fact that this is for 2.2. In version 2.3, which again is coming out here in about a month, all of these models have some kind of limited physical model attached to them. So you could go in and actually look at a dryer model, and you can actually look at the different cycles that might be available. So it goes all the way from, through the operation of a dryer where you see the tumbling motor drum. You see 1 or 2 coils coming on at any given time, and you see this, say, a 45-minute cycle where all these different pieces are coming on and off at any given time. The reason that you might want to do that is if you ever want to modify the behavior of what that dryer is doing, then that allows you to go in there and look at those individual processes and try to move and shift the processes around to accomplish whatever you were trying to do. The good example being demand response, which is really what this model is built for, so that you can do things like, okay, I want to send a demand response signal to the dryer. Well, what does that mean? You can't just turn it off and never have it come back. But some of these physical models allow you to turn it off for a certain amount of time until you get to the recovery period and then run the dryer later. The EV charger is a little bit different than the rest of them. So this represents our PEVs. And I'll say that they're a little bit different because they don't quite fit in terms of an appliance itself, but they are, because they are typically inside the home. This is where we put these models. They almost behave more like almost like a switching generator and load source. So they could almost more easily fit inside of the distributed generation sources, but we put them in here with the house. And we've created them as a probabilistic model. So not only does it represent the charging characteristics, but it also represents the driving characteristics. So it actually goes in and says, okay, what's the odds, or what's the probability of how far this car has driven before it came back to the house? So that gives you a better idea of what the state of charge is, and so therefore how much you might have to recharge it. We're not going to go into that today. When Frank comes back in I think it's in January, we discuss the distributed generation. He'll go into a lot more detail about how to use that model. The last piece that's in there that we'll talk about a little bit more, which is something that especially as power engineers we use quite a bit, are what we call the time-varying zip models. And so we use those zip models quite a bit as a generic appliance, and we'll discuss a little bit more about how we use those. So a question here is, how about the water heater? Can anyone write a model in the GLM? So right now, the water heater is represented as this physical-based model. Of course, you can always replace that with a much more generic model, like a load shape or anything like that. But the water heater is one that we spent a fair amount of time representing the physical behavior of it. So as a description, we'll get into it a little bit more detail here in a few minutes, but basically it does things like it calculates what the current water temperature is inside of the tank. You actually give it demand schedules for how much hot water you want it to draw out, i.e. representing, say, like a shower at 1 gallon per minute of hot water. That actually gets drawn out, and then of course cold water gets drawn in the bottom of the hot water, the water tank, and so that cools the slug of water inside of the water heater. So we actually track how that temperature has changed over time, and then of course how much heat is then required to heat the water back up, whether the top coil or bottom coil is coming on, so that we can look at things like, well, if I decided to do a water heater direct load control, where maybe I do a 25-degree setback on the set point inside there, we can watch how that temperature changes over time, and then gives us a better prediction of how long we actually have to use this resource. And then the second part of the question is, can anyone write a model in the GLM? The answer to that one is yes. We support what's called runtime code, so you can actually create and compile your code in runtime. You just have to have the proper compilers built in there. We use, like, for example, on Linux, use G++. On Windows side, we use MinGW. But anyone can write a model into the GLM as long as it fits into the requirements of what GridLAB-D is looking for, and that has things to do with like certain types of functions for synchronizing with the core, certain end-use structures, and a certain handling of time. I think in February-ish, somewhere in there, February, maybe early March, we're going to do a developers course, which will talk a little bit more about how you can actually write a model in the GLM. It's a little bit different connotation than actually using the current models, because you do have to know a little bit about how the actual core functions to be able to write your own models. Did that answer your question? All right, so as a way of an example, so I like to describe the ETP model that's used to describe the heat flows in the house. It's a good way of describing the complexity level that you can go into inside these models. And then it's also a good way of showing when it's good to use that complexity and when it's good to ignore it and go back to some more traditional means. So I'll give a little description about this ETP model first. So the ETP model is what we call a two-node lumped parameter model. If there's electrical engineers out here, this model looks pretty good because it looks like a nice electrical circuit. For mechanical engineers, it looks great because it looks like your standard heat flow models. But really what it is it ends up being an overdamped DC circuit with exponential decays, where you're describing the heat flows within the house, where TO right here is T outside, so the outside air temperature. TA is your internal air temperature, so what your HVAC system is trying to maintain as a set point. And then TM is actually the temperature of the mass, i.e. all the stuff in your house. So if you've ever come home from like a long weekend where you turn the heater way down and all your stuff feels really cold and it takes a little while for everything to heat up when you come back, that's because of this guy right here. But really, what we're also representing here is this UA value is basically the envelope around your house. It's basically how fast does heat transfer between the outside air temperature and the inside air temperature. H sub m, which is the heat transfer between your stuff and the air. We have things like the capacitance, or basically the thermal mass of the system. So how much thermal energy is stored in the air and the mass. And then we have things like what we call Q air and Q mass. But these are broken up into other pieces, which might be at any given time things like the amount of heat that the HVAC system is either pushing in or pulling out, depending on whether you're heating or cooling. Things like how much solar energy is being pushed in and out of the house at any given time because of how much surface area you have facing the sun. So all these things are incorporated into this model to kind of understand what's in the end, it's really trying to understand how often and how much is the HVAC system running. So you can almost think about it looking around here. There's basically a control loop that's built around these two guys. So when T-air exceeds a certain threshold, you activate the HVAC system, and it does something to modify TA. But because of these other damping elements, it has different behavior than if you just put that into what's called like a single node model and try to push that energy around in that way. So it's effectively what we're trying to do is we're trying to balance simplicity and complexity. I personally think we've done a pretty good job of it because it's simple enough that there's a direct analytical solution. We don't have to try to do numerical approaches. So it makes for extremely fast computations because it's only a second order differential equation. You can go and look at say like building simulators. So I'll use a DOE example of Energy Plus. Great simulator, great tool. Uses multi-order differential equations, has thousands of settings, which is looks great to a power engineer, or excuse me, to a buildings engineer. But as soon as the power engineer looks at it, it's kind of like the eyes roll back in the head. So we've tried to make this simple enough that we can use it from a power system perspective without over-swamping the complexity that could be seen from a mechanical engineer's point of view in how the system operates. So we think we've captured this balance. We account at least enough things for things like weather and thermal properties and solar and internal gains and thermostat settings. But we've left off a lot of, say, the extremely complex control systems that you would see in, say, a commercial building. So you don't see things like water-cooled systems or like multi-zone models or anything like that. So effectively, this is designed to represent a residential building, something on the order of anywhere from 500 square feet to 3,500, 4,000 square feet. Beyond that, this is not the right model for it. But because of the simplicity of it, we can do a lot of them really, really fast. And the key being that when we start to model things like a feeder, which may have, say 2,000 residential homes on it, you don't want something that's calculating 2,000 eighth order differential equations to try to get you moving forward in your simulation. So that's really the goal here, is trying to balance these two different things. To give you kind of a little example of what these things are doing, it's basically doing heat balance equations. We're trying to balance out all the energy flowing in and out of the system, where it's coming from. But really, it comes out to this second order differential equation that has two components. One term is looking at kind of the longer mass effects that, as we say, govern kind of the demand response effect. So, if I'm going to shift my thermostat by 5 degrees, what's the effect of that over the course of the next hour, 2, 3, 4 hours? And then we have a second term that kind of drives some of what we'll call the shorter term mass effects, which are basically governing the 5 to 10 minute air conditioning cycle. So basically your duty cycle of your air conditioner. And what GridLAB-D does is it basically goes through and it solves these equations at every state change inside the house and says, well, okay, I just turned off. Well, if I look at all these equations and I predict forward, when should I plan on turning back on again? And so you end up getting what looks like effectively a duty cycle. So you can see here in this example here, you can see the HVAC system coming on and off. You can see where in this example, it was obviously a cold morning, so the heater came on, and you can see it cycling to maintain the temperature. Right here represents where the user came in and said, "Oof, I want to take my shower. It's cold out. Let's turn the heat up by 5 degrees." So you can see that it actually runs for a solid amount of time until the temperature gets up to where the user wants it. You can even see some variation here in the way that the amount of power being drawn out of this heater is being driven by things like efficiency is driven by the outside air temperature. So basically on a heat pump, how if it's really cold out, you can't extract as much energy out of the outside air. So you see some of these temperature variations and about how much power is actually drawn from the unit. Then down here you can actually see things like the fact that the red line here is with the heater running at 100 when the voltage is set to 125 volts, and the blue is representing when it's set to 118 volts. So we captured things like the fact that, say, a resistance heater, when you lower the voltage, instantaneously you consume less power. So you can see there it's probably different by a couple hundred watts. But that means that the heater actually ends up having to run for an extra amount of time because it still takes the exact same amount of energy to move you from, say, 71 to 70 degrees. And so we're trying to capture all those effects in there. So not only the temperature and climate effects, but also the power system effects, which end up being, how does voltage affect the efficiency of these devices. Here in this picture, you can kind of get a conceptual view of what's going on. So if you look at the black dotted line here, this is the temperature of the mass. The red one is the temperature of the air. Basically what's happening here is this set point is 60 degrees, and then right here it gets bumped up to 70 degrees, and then it's released back to 60 degrees. But you can see the fact that, when you get down here, you can see the air temperature is toggling back and forth from the bottom to the top of the deadband, which is how you get your duty cycle here. And then when this user activates the heater and says I want it to be warmer inside here, you can see that the air temperature gets up very quickly, but it takes a little while longer for the mass to catch up, and always trails a little bit behind the change in the air temperature. So these are just kind of a view of why we're trying to represent this way. Now I'm going to take a second and kind of, if you're not a buildings person, this is going to kind of roll your eyes back a little bit, but I just want to kind of give you a view of how complex this model could be if you wanted it to be. And then I'll go through and show you a little bit some of the ways that we've looked at reducing it from the user's perspective and making it a little bit easier to use. But when we look at using this house, there's literally, I think at this point, somewhere in the neighborhood of like 350 parameters you can set. It goes all the way from things like physical design parameters, like ceiling height, how many doors does it have, what's the insulation on your roof versus your doors, how many windows do you have. It's things like, what are my HVAC design parameters? So, when the person came in and sized the HVAC for the building, what defaults do they use? So what was my cooling design temperature? What was my, record high temperature? What is my coefficient of performance? So basically, how efficient is the HVAC? We have heat flow parameters. So things like, what's my internal gains? How much solar gain do I have? How much energy can my mass store? All these different things. Fan and motor parameters. Like what's the efficiency of my fan? How much power does it design? Is it what's the zip fractions on it? Sorry, looks like there's a typo right there. I'll get that fixed. Things like thermostat parameters. Some of these are pretty useful, heating and cooling set points. But a lot of these you may never actually see, last mode timer, things like that. Derived parameters are all these kind of things that are used to calculate the state of the system. So, what's the air temperature versus the mass temperature versus the outdoor temperature. What are air volumes and masses? All these different things. Lots of it, things like zip fractions. Now you can say, what's my peak demand at any given time? What are my breaker amps? What is my power factor of each of these devices? We can set a number of different types of enumerations in here. So, for example, what type of heating system type am I? Do I want resistance, heat pump, or gas? Cooling system, is it heat pump, standard electric, or none? things like, do I have an auxiliary heating system? What type of auxiliary strategy do I use? What type of glass do I have in my windows? All these different things. We even have some limited ability to do motor modeling. So, do we want to represent the efficiency of the HVAC motor, which is important for CVR studies. But really, that ends up being a whole lot of stuff that can be a little bit difficult and a little bit intimidating to use. So these are what I call my easy house major parameters. And these kind of go up in layers in complexity. Literally, you can just say something like object house. That will create a house with all the default parameters in it. Every value inside of the house model has a default associated with it. And even more than that, it has a reasonable default associated with it. So for example, if you don't put in floor area, it defaults to 2,500 square feet. So, so in the case of where you wanted to use to not use any parameters, it would just default to these values right here. As you're going up in levels of complexity, then we can go to things like, so for example, we've put in what we call a number of thermal integrity levels. These are basically broad representations of all the way from low efficiency homes to high efficiency homes, again based around US standards. And these basically say, if you give me this, then I will configure this house so it has all these different settings so that I get a house that is super efficient versus very low efficiency. Another important one is kind of cooling and heating set points. So especially if you're doing demand response studies, these are a lot of what you're going to be driving, say moving this around on the thermostat. So we've made these available. These kind of go into my easy house. And then we can go one layer of complexity further, where instead of calling the thermal integrity good or bad, for example, we can actually put in these values of what's my insulation? Do I know what my how much insulation I have in my attic? Do I know how energy or how sealed all the windows and doors are and things like that? You can even go as far as number of stories, which is can drive has some importance on there. And then of course specifying your cooling and heating system types. So I would say about 75% of the time when we're using this model for our studies, this is about as complex as it gets right here. And this kind of gives us enough freedom of movement to kind of make the models complex enough that we want to do with them without bogging it down with too many settings. Any of the defaults that are not put into the house that you've created are fed off of these values. So for example, if you when you activate a house that say has very good insulation, it will make the size of the HVAC unit smaller than if you put a very low insulation, or excuse me, a low efficiency model in there. And the reason being is because it takes the less efficient the house is, the more energy it takes to keep it, say, cool in the summertime. So there's a standard sizing that goes with certain types of homes, and so it will adjust to that. So basically, if you change any of these parameters inside here, it will change all the defaults because all the defaults are built off of kind of a cascade of these values that you put in there. So that was kind of the quick 10-minute dirty house explanation. Were there any questions here before I move on to some of the other residential end-use models? Okay, so we'll move on. So as I said, the other side of the residential module is the what I'll call the end-use models, the appliance models, or any slew of different names that you want to call it. But the first we want to talk about is what I call the implicit models. So built into the house model itself, if you don't want to deal with other appliance models at all, if you're just focused on HVAC, for example, and you may not want to spend time working with how you would put in, say, for example, the hot water heater. Maybe you don't care about the operation of the hot water heater, but you do want to capture the effects of the heat that the hot water generates or the load that the hot water heater generates. So built into the residential module, specifically inside the house, we have activated what we call implicit end uses. And these are basically default load shapes. So they basically go through and they use what we call the LCAP load shape data, which LCAP was a study in the Pacific Northwest back in the late 80s, early 90s. It went through and monitored all the circuits on thousands of homes, and we're able to kind of get a statistical representation of what the average appliance load shape looks like. So for example, you can go in and you can activate implicit end uses lights and plugs. This little, the piping symbol means and in this case. So here we're going to activate lights and plugs, and it goes through and it pulls that LCAP load shape data down and feeds this into the house so that you actually get the load shapes of the lights and plugs added into the overall load of the house. But more importantly, it also adds the heat effects into the house, which if those are not accounted for, then your HVAC system behaves kind of oddly from what might be expected. By default, all of these implicit end uses are turned on. So if you just put in module residential, and that's it when you activate the module, every single house in the model would have every single implicit end use. That's not typically the way we would use it. In fact, normally what we'll do is we will put implicit end uses none, or implicit end uses maybe just a couple of the load shapes, because in the end, most of our studies are going to represent hot water heaters and HVAC systems as standalones with the physical models, so we don't want those load shapes to be double counted effectively. You can put together as many of these as you want. I think there's 11 different models in there. I think we get back to them here in a second. I list them all out. But these are kind of, again, since these are activated at the module level, not at the object level. Basically, I'm just saying, kind of be very careful about those and think about whether those are what you want in there or not. When we get down to the examples later on, we'll show you the 3 or 4 different ways that we do or don't use these. So a little bit about the residential end uses. This is the structure that supports all of the different appliance models. So basically all the appliance models are built over this structure so that they all have kind of a common format. So for example, here I use a object lights example. And the reason that I bring this up is mostly because when you go to use things like mod help, which gives you all of your different solutions if you want them, it's helpful to be able to go and to find the, when you want to go be able to find the parameters that you're looking for, it's helpful to know where you find them. So let me bring up this as an example here really quick. And give me just a second. I have to find a good executable to work with here. So for this example, I'm using the executable that I distributed with the Module 1 online tutorial. We'll just go to that directory. And of course, like I said, in the first class, we can use mod help, which is great for trying to look up different variables. So in this case, we're going to look up residential, let's do lights, since that's the example we're using right now. So you can see a whole slew of stuff gets printed out here. Let me resize this real quick. I apologize, I usually have this set up a little bit better. I had to wiped most of my computer last week, so I'm still kind of recovering everything here. All right, let's see. It's a little easier for everyone to see. So we see here when we look in the module residential, we have things like default line voltage, default line currents. These are all the residential level pieces. And then we look at things like the class lights. Here's all the lights level pieces. But you notice that there's this other little piece, the parent residential end use. And this is class residential end use. So all those pieces come out of the structure. Well, there's these other pieces here that are dependent on the actual class lights. You'll see that I've kind of broken this up here in the slides to talk about that. So, for example, power factor, heat gain fraction, installed power, all these pieces are part of the residential end-use structure, not part of the lights object itself. And what that allows you to do is set things like the power factor, lets you set things like the zip fraction, what's the rated power of whatever you might be using, whether it's, if it's lights, that's a pretty obvious one, it's 2 kilowatts of installed lights. But then also things like heat gain fractions, so what percentage of the electrical energy that you are using is converted into heat energy. And then it has some of these kind of calculated values that are basically, because of that, what is the actual heat gain that you're getting? How much power are you consuming at any given moment? How much energy have you consumed over a given time frame? And what was the peak demand of this appliance? Things like that. One thing to notice in here with the residential structure, again, because this is based off of buildings type of approach to modeling, you'll notice that while in power flow, everything is based off of watts. In the residential, everything is based off of kilowatts. You always want to be careful when you're doing things, when you're doing recordings, and you are piecing together different pieces of information. These two different modules have kind of different flavors because of the different approaches to them. So always be careful of that one. You'll notice that almost everything in residential is based off of kilowatts or kVA in this case. So just be careful of that. There's things in this residential end-use structure, things like voltage factor. This is basically, is it 125 volts where you get a voltage factor of 1.05 versus 120 where you get a voltage factor of 1. And that's a way to do your correction on your zip fractions. And then down here, this is actually the posted amount of power at each of these type of zip fractions. One thing I didn't mention up here, there's a couple here that I didn't mention. Breaker amps. Normally this is not important. So for example, object lights will default to, I think like 50 amps on the breaker, which is usually not an issue, so you don't even get close to that. The one time you can sometimes run into problems with that is if you're using what I'll call a generic zip load that we'll talk about later, where maybe you're trying to represent all the load inside of a house at once with just a single value or just a single shape, which of course then means at any given time you may have, say, 1 to 2 kilowatts or even 3 or 4 kilowatts of load. But because this breaker amps defaults to 50 amps, that's a lot more than 50 amps, and so you end up getting breaker trips on there. So normally you don't have to engage this value, but every once in a while you may have to, and it does throw warnings if that happens. And then this load shape, any of these objects that you create, say for example object lights, you can feed the shape with a load shape. Or you can feed it with, say, like a schedule or any of those pieces that we talked about a couple presentations ago. But again, I'll show you some examples here in a second because these are a lot easier to work through with examples than trying to explain them. So for example, here in this one, we're creating a class, or we're adding a variable class lights, and we're adding a shape that I'm just calling my shape. In this case, I didn't even represent the shape. But then in this object lights, we're creating my shape. In this case, we're using a type analog, so just a straight, smooth representation. We're using some schedule. and we're going to specify the amount of energy that we want it to consume over a 24-hour period. So we basically put this in here, take this, it will multiply it by the schedule, and it will try to adjust the schedule's output so that we get this amount of energy over the course of the day. We do things like, say, okay, what's the maximum amount of output that this shape can have? So in this case, 1 kilowatt, because it's the installed power. We tell it what power factor it is, and we tell it what the zip fraction is. So in this case, this is, basically representing incandescent bulbs. We can also do things like place them indoor versus outdoor. In the case of lights, that's pretty specific to lights because if your outdoor lights, while they consume just as much power as the indoor lights, they definitely don't affect your HVAC system the same way because they don't dump the heat into the house. So that's kind of the general end-use structure. So all these appliances that I'm now going to talk about fit over the platform of this end-use structure. So basically, you can think of those as the residential end-use as a parent class, which then allows all these child classes to pull information from the parent class, plus they get a whole another layer of information that they're allowed to access because of the specific model. So right now, these are all the different models that we are representing in one form or another, and we'll go through each of them very quickly and briefly, and I'll tell you what state each of them are in. But these are the 12 models that we're roughly representing right now. So as I said before, water heater is a physical model. All these ones, lights, refrigerator, clothes washer, dishwasher, plugs, microwave, range, freezer, dryer, all of these are load shape driven models that we are slowly converting into physical models. So by version 2.3, we should have, I think, about half of these converted over into physical models, or you can still use them as shapes. So we're always backwards compatible with that. We talked about EV charger a little bit. And then one that I didn't talk about is the occupants. This is basically a way to represent how many people are in the home. So specifically, it's how much body heat do you generate. So one of the things, especially with commercial buildings, which is a really important piece, but also for residential, is the fact that depending on how many people are inside the building, each person generates about 300 watts of waste heat. So you want to account for that heat energy inside the building because it drives how the HVAC system behaves. A little caveat on that, and this came up on the forums a couple weeks ago, is that the occupant load, that's all it represents. It's just the waste heat of people. It doesn't actually affect how the other appliances behave. So it's not a kind of like a big block. Occupants are here now versus not here. So it doesn't affect how say like the clothes washer behaves because there's 8 occupants here now versus later. So I'm going to kind of go through each of these models, some of them in more detail than others. Some of them I'm going to just flash through really quickly, just to kind of give you an introduction. Of course, you have these slides available to download. So if you want to look back at them later, you can of course download them and get a little bit more detail. So I'll spend a little time here on the water heater because it is another physical model. But basically, the water heater uses 2 models. Switching the models depending on what state it's given at any given time. Roughly, you could call them the 1-node and the 2-node model. The 1-node model, pretty straightforward. It's kind of a simple lump parameter model. It's where what we call the slug of water within the entire tank sits at a uniform temperature. This is basically when you're just sitting there. Basically nobody's drawing hot water. You're just trying to maintain the current water temperature inside of the tank because of the losses of heat across the jacket. So you can make that a very, very simple model. The 2-node model, which is what we use when we're trying to represent the flow of hot water in and out of the tank, or hot water be only flowing out of the tank. But basically, we're trying to decide what should the model look like when there's a partial state of depletion. And so basically, what happens when you start looking at a hot water tank, and you have cold water flowing in the bottom and hot water flowing out the top when it's turned on. And what ends up happening is you actually end up getting a separation between the two heat zones. So in the top you have effectively what we call a hot slug of water, and on the bottom you have a cold slug of water. There is some mixing in between, but for the most part there's very little mixing of them while the hot water heater is in actual use. So we have what we call the upper hot node, and we have the lower cold node, where the upper hot node is at the water heater set point, or whatever current temperature it was before the activation. And the lower slug is actually the inlet water temperature. And so what we're really tracking is not so much the temperature of those two individual slugs, but what is the boundary between those two slugs, and basically what's the height of that boundary. And that height of that boundary, since we know the temperatures of the two different slugs, means that we also know what the total energy stored inside the hot water heater is at any given time. So when we're doing these, when we switch to the two-node model, which is any time that a water draw schedule is given, we're calculating what is the actual physical movement of that boundary. So the way that we interact with this and actually move information in and out is we do a number of things like declare what are all the different physical parameters of it. So, what's the tank volume? What's the insulation on the tank? How big is the tank? What's the heating element capacity? Is it a 4,200 watt versus a 5,000 watt? Notice again, residential, almost everything is in kilowatts, so be careful. One thing to always remember is you could always specify this as 5 kW, or you could specify it as 5,000 W. If you add the units at the end, GridLab will convert to the correct units for you, so you don't have to worry about it. We can do things like what type of heat mode is it? Is it a gas water heater versus electric? Is it in the garage, or is it actually inside? Which basically affects how much heat gets dumped into the house, but also then what's the differential of temperature between the tank and the outside jacket of the hot water tank. Things like set points and dead bands, current temperature, current what we call height, which is again the height of this boundary, and then the load, the actual load at any given time. Because while we have a heating element capacity of say 4.5 kilowatts, this is a resistor, so at any given time, if say the voltage went from 240 to 220, so we've dropped by 10%, then the actual load goes down also. But then to actually decide when this hot water heater is operating, we have what's called water demand. And this is declares basically how many gallons per minute of hot water are being extracted at any given moment. And to kind of give you an example of what this might look like, so if we look at the temperature inside the tank, you can see during this period of time, this is your kind of what I call standard decay. So basically, it's the loss of heat from the slug of hot water. It's radiating out through the jacket out into the external air. So you can see this temperature decaying right here, and then there's a little bit of a request for hot water. So this is at say 1 gallon per minute. So this is something like maybe you activated your kitchen sink. We're actually washing dishes for a couple minutes, and so you can see it immediately activates the hot water to drive it back up to the higher temperature, and then of course we decay again until we hit another activation to say we want it to come on, and you can see how this the temperature of the tank is kind of moving along through time, and of course then you can see the different pulse train of the actual load activation. So of course you can see here we actually went more like a 5 gallons per minute, which is more like we turned on the dishwasher or the clothes washer, or maybe took down here we took a shower or something in those range. You can see that affects the overall amount of energy that is consumed. So while it runs for the same amount of at the same level, this model is obviously not taking into account voltage, but we can see that it has to actually run longer to maintain the temperature. Another thing to notice here, this green line here is what we call the height of the slug. So again, we can see as we're moving along here, this is in basically steady state that this is the one node model. And then there was an activation where there was actually water demand. You see a drop in the height of the slug of hot water, and then it slowly recovers over time. So this kind of gives a description of the way that the hot water heater tank is designed to work. Of course, one of the big questions that will come up is, well, that sounds great, but where do I get all this information? So there's a couple ways. So first off, if you're looking at your physical parameters, most of these can actually be gotten from your water heater design. So when you go, say, you can just go to, for example, Lowe's.com and look up your nearest friendly hot water heater, and most of these values are specified. If you don't know it, then there's good defaults built in here. So, for example, inlet water temperature defaults to, I think, 58 degrees or something along those lines, which is pretty common for the average of most groundwater, if you look at the average throughout the course of the year. The big one here is, of course, water demand. How do you get this schedule of hot water demand? So there's a few sources out there. DOE has some test models that you can use that are actually like test draw schedules that are kind of very, very rough averages of how much hot water is consumed over time. CSA, a Canadian company, also has 3 schedules, CSA A, B, and C, that kind of have different, what they call emergency levels of how much water draw. They basically represent like a 2, 3, and 4-person family. The problem is that those are very average shapes. Again, they're kind of like the LCAP shapes. They kind of give you hourly averages for how much they think will be drawn. The piece that's missing is these actual individual pulses. So we've provided a couple of ways to kind of look at this. So for example, if we look at, I think I have it on here. Let me double check. So if we go into the modules that we've given you, so I think in the IEEE 13 node model, for example, there's a water and set point schedule. Pull this over here. So you can see we've kind of put together a few schedules that represent events effectively. So you can see this is down to this is using a schedule. This is down to a 10-minute resolution over the course of 24 hours. And you can see most of these values are 0, obviously. But then we have what we call events. So for example, at 5:50 in this one, somebody got up and took a shower for 20 minutes approximately. And then combining these schedules with a number of things like schedule skews and the linear transforms, you can get a pretty rough approximation of what this might look like. So for example, the schedule water 1 is built using the probabilities from the DOE hot water shapes. We treat that curve, that kind of average curve, as a probability of an event happening. And then from that, we decide that these events will happen at a given time, and they'll be of a certain intensity, representing things like a 0.61 is probably something along the lines of a low flow shower, or something along those lines. So whereas we come down here, 0.92, 0.3, 0.78, this is more like a dishwashing event where someone washed the dishes in the sink, put it in the dishwasher, and then started the dishwasher. So we try to represent all these events kind of in that way, so that when you look at each of these different schedules, and I think there's 20 of them in here, there's a lot of them, I think 20, that while any single one of them does not look like these kind of average load shapes, if you put them all together into a big model and you kind of and you use the schedule skews that we show examples how to do in this IEEE 13 mod model, the shape ends up looking almost exactly like these kind of general average shapes. So all that's to say, yes, it's very complicated. It sometimes will be more information than you might want to include in your model, and that's kind of up to you. It's depending on how complex and what you might want to do with the model. If you do want to use these, and I always really recommend that you do use the hot water heater models because they are typically the second biggest load in the house. You can use any of the information that we've already provided out there of how to create those schedules. It took a long time to figure those out, so don't try to repeat it yourself unless you have experience in doing that or want to do it. So moving on to some of the other appliance models, and I'm going to go through these pretty briefly because most of these are actually coming out in the 2.3 version here in the next month. So dishwasher, we have these things that basically we can specify all the different component powers. What is the daily demand? So this would be the load shape. What's my baseline energy consumption? So when you buy a dishwasher, it says consume 2.1 kilowatt hours per run and things like that. So by using these, you can specify the entire you basically specify the entire cycle of what this dishwasher might look like. So when it comes out, your dishwasher looks a cycle like this. Basically, you're kind of doing things like you're turning on some of your motors, so you're pumping in the hot water. You cycle off and do some control things. You basically have this big spike that ends up being the coil powers, the heater coils coming on to heat up the water. And it basically goes through this entire process. Very complicated, but it represents kind of all the different control aspects that are inside that dishwasher. The reason you might want this is because say that you want to do a demand response action that will put this dishwasher into a more efficient mode. What you can do is do things like deactivate these heater coils. So this right here represents the time where the heater coils are basically heating up, and there's a fan that blows hot air across all the dishes so that they'll dry faster. Well, there's certain demand response characteristics that say, well, you don't necessarily need this, or you can spread them out over a longer period of time at a lower value. Because this model is represented by all these different states and the changing of all these different states, you can actually go inside there with an external control. For example, you could write it into your GLM as a runtime class. You could modify what that control looks like and tell it to basically behave in a slightly different manner. That's the reason behind having these in this way. Before I get into the next one here, let's go ahead and take about a 5-minute break here. One, I need to take a cough drop because I'm starting to lose my voice. But two, that'll give everyone a chance to use the restroom or take a quick break. So let's just take a quick break. I've got 9:19 right now, so let's plan on meeting back here at 9:25. And like I said, I'll be grabbing a cough drop, but if anybody has any questions, go ahead and type them into the chat window there, and after I get done grabbing that cough drop, I'll try to answer them if any have come up so far. All right, so we're coming back in line here. But everyone probably saw was chatting here on via the forum through about some of the GUI possibilities with GridLAB-D. So since we have a break here, this is probably a good time to just talk about it a little bit. There's, as everyone's probably figured out at this point, there is no GUI for GridLAB-D. It is a pure text interface. So all the models are loaded into the textual GLM files. All the commands are done from the command prompt. And so it's not exactly intuitive to use. And in fact, in a lot of ways, can be extremely difficult to use. But part of that is, there's this balance of, do we try to make it look pretty versus do we want it to, did we want to develop more features? Because it's always balanced about, how much time and how much money and et cetera, et cetera. One of the things that we've always envisioned is how we could actually try to build that GUI on top of what's supported here. So we've had a couple of initial starts and stops that have tried to address some of those things. What we've decided now, at least from the P&L perspective, we have no plans on developing a GUI directly. But what we'll do is we are planning to support anyone who is but we're planning to support anyone who has a desire to do a GUI. So what we've done is a lot of work on the API sitting in the background, so that you have more access to the variables, and so that we're no longer kind of in the job of trying to create the GUI, but we're trying to work with the interface to try to help move that along. That said, if anyone wants to create a GUI, I'm the first person to say, please, please, what help do you need? So Paul, well, you may not be able to hear me, but you don't have sound as in like you can't hear me or you can't talk. So I got a message from Paul here that he can't hear me. Is anyone else having problems hearing me? All right. Well, we'll go ahead and get moving forward here. Apologize, Paul, if you can't hear me. Like I said, these things will be. We are recording this, so hopefully we'll be able to post it online for you afterwards. So moving forward a little bit more, I'm going to go through these next ones really quick because unless someone has specific questions about some of these devices, just stop me and we'll pause for a second. But otherwise, I'm going to move them through them pretty quickly. Again, dryer is the next object that we support. Baseline energy, different modes, whether it's just the controls, whether it's just the motor, different dryer coils. Again, the idea being so that you can represent it in some way like this, where you can see you have a long initial cycle, and then maybe you have a bunch of pulses and things like that. And so what you're able to do is kind of define these different pulse lengths and cycles, and get the kind of the dryer represented in this more of a what I call more of like a state physical model. Again, we're supporting things like the range oven, range and oven. So here's all the different enumerations for the oven. Here's all the different enumerations for the cooktop. once again, the idea of trying to represent kind of the pulse trains that occur, that you can do things. I think this is the oven, for example. You can actually see the cycling of the temperature inside the oven, bouncing back and forth. Cooktop, you can see it coming on in different cycles where it's on, and this might be something like setting 6 for people who have digital ones, but it's on at 2 kilowatts and it drops down to 1 kilowatt after it's gotten the first initial heat up, and then it kind of has this kind of gradual afterwards. Things like the refrigerators, we can do things like, how often does the door open, what state is it in, whether it's, the compressor is on or off, is it in defrost mode, kind of these different things. What's the defrost delay time, for example, like if we're going to delay defrost because of a demand response signal. And really that ends up just something to look like a pulse train, where you end up getting a pulse train of compressor cycles, and then you have these longer periods where it's doing what's called pre-cooling before the defrost cycle. So it actually cools the refrigerator to, say, 2 or 3 degrees cooler than normal, and then runs the defrost cycle and lets it heat up to 2 or 3 degrees higher than normal. Clothes washer, we have some things for the clothes washer also. Again, just trying to represent the power draw that's coming out of that. Lights. And so for lights, for example, we have things like the type of enumeration, the type of lights that it might be, whether it's an incandescent versus CFL or fluorescent. We can do things like, and what those do is they set, say, like the power factor and the zip fraction. You can do things like power density, so what's the watts per square foot, that you can specify it the same for all houses, rather than trying to specify each one's installed power individually. You can even do things like circuit split. Are these all on one 120 volt circuit, or are they split across 2 220 volt circuits? Just a second here, guys. Sorry, guys. I'm trying to see if I can fix Paul's sound here. So, and then similar to lights, we also have plugs where we can define the installed power, use the load shape, and things like that. Back again to occupants we talked about before. So with occupants, although I will notice there was a note that if you look at the forums, there was a bug in version 2.2 on this, but it is fixed for version 2.3. Basically, you specify the number of occupants. So, for example, maybe this household has 4 people who live there, and then as a schedule, you would specify the number of the occupancy fraction. So, for example, maybe 0.5, which means 2 of the occupants are there, and then an average heat gain per person. Again, microwave, freezer, these are, as the note says there, these objects are very much in the development stage and aren't even going to make it fully into the version 2.3. Great. Okay, can you hear me now, Paul?
Yeah, I can hear you.
Okay, good. And then we move on to the final one, which we spent a little time in this one because it's a great one to describe the way that all these different models work. But it is our generic, what we call zip load, and really it's a way of specifying any component of a load that you want to do in a very simple way, or at least I hope so. really what it ends up being is you define this variable called base power, which is effectively the load shape. So you can define this in terms of a schedule. You can use a player file. You can use a load shape. Whatever you might want to use in there, you can put that into base power. And this represents kind of effectively your rated power. And then on top of that, you can also specify all the power factors for each of the zip fractions. You can, of course, specify each of the zip fractions. And then what that does is basically through those, it calculates the actual power draw at any given time as a function of voltage and what other pieces you might want to put in there to have it dependent on. It also has things like a heat fraction, so what percentage of the consumed electrical power is actually converted to heat energy. And then this actual power, which is the converted after you apply the zip fraction, how much do you actually get out of there. This is actually the one that we use quite a bit. Because it is so generic. So the standard model we'll put together for most of our studies will be the house with an HVAC system, a hot water heater as a standalone load, and then a single or maybe two zip loads, depending on what we're trying to represent, that kind of are representations of all the other stuff. And mainly because, when we're looking at some of these studies, say, for example, demand response, while there are certain times we may want to do things like a dryer or other devices, most typical ones are HVACs and hot water heaters. Second, let me. So what we can. So basically, what we can do is then kind of lump these all into zip load. If we want to represent more complex ones, we can. But for the most part, for demand response and CVR studies, the zip load is good enough, basically. You kind of capture the thermostatic loads by capturing the HVAC and the hot water heater, and then the zip load captures all of the kind of non-thermostatic loads, and for the most part, captures the end-use behavior well enough. So really, for me, the best way at going through these and understanding how to use them is through the exercises. And what I'm going to do is I'm going to try to go through some of these on the phone here, probably stick to about 20 minutes here or so, and allow you guys to ask questions as we're going along. And if you have any, please let me know. And so again, sorry about that. So with these, with the module 3 that is now out on the SourceForge account, again we have demos and solutions and things like that. So this first one we're going to look at is basically we want to activate all the end uses, and just basically look at the power output. So if we go into these residential solutions, we can see there's an exercise already built here for us. I'm just going to go ahead and grab all of these and move them over into my release folder here. Pull this up. And so just kind of walking through the model here a little bit, just kind of show you what's going on. Of course, we created a tape module because we want to be able to record information out. We've activated the residential module, but we're not at this point activating or I should say deactivating any of the implicit end uses. So at this point, all of them will be activated. We've also turned on power flow and climate. We activated our clock, and we're just going to run this for a week here. We've turned on a climate file, and this one in particular is the Yakima, which we use a lot because it's 45 minutes away from us, but also has a very a climate that's very up and down. So during the summertime, it can be 105 degrees. During wintertime, it can be 0 degrees Fahrenheit. So it's nice for us, it's a nice test model that we like to use because it kind of flexes the model a little bit. Here we've created a triplex meter. So remember, this is the interface between the house object and the power flow. It's also useful because triplex meter allows us to do things like capture energy usage or do billing. So if you assign a value to the energy consumption, whether it's real-time pricing or time of use or fixed price, this triplex meter can calculate the energy consumption and also calculates the bill for this particular house. But it also acts as a way to connect you to the actual power flow system. And we'll see that here in a couple of later examples. But here you see there's this object house, and of course we're connecting it to a 120 240-volt circuit, in this case on phase A. We've activated a heat pump heating system with an electric cooling system, which is effectively a heat pump with central air. There's some auxiliary strategies that are going off. Our system mode, which is the current mode it's in, basically saying that this thing is starting in the off position. And we're kind of initiating some of the things, like we're starting the initial air and mass temperature at 60 degrees. Here's our set points, 1 story, a few different things like this. But really what we're going to do is we're going to run the recorder here, and we're going to capture total load. So if we run this, so it ran, and ran fairly quietly, so that's usually a good thing. So we'll take a look at the results here. See, there was an output here that was obviously not named with the correct convention anymore, but we'll look at it anyway. So if we look at it, this is the total load in kilowatts of the household at this time. So what we'll do is just do a quick graphic here. So this is what over the course of the, I think I ran this for a week. This is what the load shape looked like for a week, measured on 1-hour intervals of the actual power. Now, of course, one thing to be careful about when you're looking at the total power, those are instantaneous measurements and not energy measurements. So in this case, it's running every hour. So there's always chances that you can capture a period where the entire HVAC system is on. In this case, it's a resistance coil heating unit, so it's not really having a 12 kilowatt resistance coil heater is not that common, but it's a setting that you can do on there. And so then if we let me just save this really quick. Test file. And what I'll do is I'll go ahead and come back here to this model, and let's do something like so for example, this is air conditioning that we're running on. So let's do something like make the cooling set point more like 65. So we're going to really reduce this. So I think this date is a really hot day in July. I think the temperature is sitting around about 100 degrees. So we're going to put this cooling set point of being really something very low, just so we can kind of see what the effects are here. So we'll save it and rerun it. Okay, and then we'll just import this into here. So I'm just grabbing these and putting these 2 columns side by side so we can kind of look at them and see the differences. So you can see here by affecting the cooling set point, we actually affected the behavior of the way the system worked. So because this cooling system was set to be at a much cooler temperature. You can see that it's running more often. In fact, if we had measured the energy in the triplex meter, we would have seen that the measured energy over that 7-day period would be a lot greater in the second case, in the red case there, because you have a lower set point, so you're operating in less efficiently. So what we can also show is, so we can do something like this. We can set the cooling set point to, say, absurdly high, like 95 degrees, and we can set implicit end uses to none. And then, of course, rerun this thing again. Hopefully I closed it. And so this should have produced the output again, and just replace the one that I had there. So load that up, and now we can see that basically the HVAC comes on a couple times to keep it below temperature, but then you can see there's almost no base load here whatsoever. That's because we turned off all of the implicit end uses. And so that's really all we're trying to show here is kind of the effects of these implicit end uses and the different aspects of it. So that's a model that that everyone should have available. I recommend playing around with that quite a bit, just to kind of just go in here and tweak values and compare it to the last one, kind of get a feel for the way that this works. Of course, with the point is really just to kind of get comfortable with it and understand that each of these things have different effects. What we also want to do is kind of say, well, okay, so what else is there in there that we can kind of look at? So we're going to go back in here. We're going to add in a couple things. So, for example, I'm going to change this to no longer be every hour, but I want to look at these at, say, 15-minute intervals. And then I'm going to correct this number, too, because it's driving me nuts. And then we will do things like we can come in here. We can also add in not just total load, but let's say we want to look at the internal air temperature. So this is the actual air temperature inside the building at any given time. We can also even come up here to, say, triplex meter. And let's do this. This is kind of a good example, too. We're going to switch to a multi-recorder. So if you remember, a multi-recorder allows us to look at multiple objects and record across a bunch of different ones. So in this case, we're going to name this house. So here we want to say, I want to look at house 1's total load. I want to look at house 1's air temperature, but I also want to look at my triplex metered measured energy, I think it is here, real. Let's double check that. So again, we can always use mod help. So here we're going to go to mod help, power flow, triplex meter. So it lists out all these different values so we can see measured real power is what I want to look at here. Excuse me, we want energy. So if we look down here, it should be a measured real energy. What we want to look at is the actual amount of energy this house is consuming over time. So we can look at the actual integral of this house 1 total load. Let's go ahead and turn this back on. Run this real quick. Make sure I didn't make any mistakes. Okay. And then we can look at the output on here. So now you see we have a number of different columns that we can look at. So for example, we'll go ahead and plot all of these. much because we want to switch this to a different, sorry, hold on, different units. So again, measured real energy is in watt hours. Total load is in kilowatts. That's why we're having a hard time seeing these. So let's do this here. Pop that out here and just do this guy as this times 1,000. So we can see here your total load over the course of the day is kind of going up and down, but your energy is an accumulator. And then we can also take a look at, say, like the air temperature over the course of the day. So of course in this model, I forgot to set it back, but we're setting it to the temperature of 85 degrees. So here, let's do this again and go back and use a reasonable temperature this time for the cooling set point. Go take it back to 75. Let's do 70 here. All right, let's try to run this again really quick. All right, so if we take a look at the output, and this time we'll just take a look at air temperature and power output. Switch this over to the other axis. So you can see here, of course, remember we were trying to maintain the air temperature at 70 degrees. So you can see here it was at night it was drifting up, or it was drifting down, and then as the air temperature the outside air temperature came up, our inside air temperature came up, and we can start seeing that it's trying to maintain it around 70 degrees. So you can see it kind of cycling on and off, and then down here in the power output, you can actually see the duty cycles starting to cycle on and off. Let's zoom in on one of these. Where to do that here? Let's just do this. Grab 2 days really quick. Sorry, I try to remember how to use Excel here. Hence the reason it'd be nice to have a GUI if anybody's thinking about that, because it'd be better than trying to work with Excel sometimes. So if we just zoom in here on 2 days, we can take a look at this. And again, we'll swap this to the other axis. So we can kind of take a look at the way that, we can see as the air temperature hits the upper deadband, it's cycling the HVAC on, and we can see the load decrease, or the air temperature decrease, and then it turns off, and air temperature starts to increase. And we start to get the cycling event. Down here again, you can see the base load shapes that are being used also. So that's just kind of a quick show of how these things work, and really what these models are designed, these test models that we've given you here, is to really just kind of go in there and play with these. Start changing the settings, start to get the feel for the way these things move around when you change different settings. But the one that I really kind of want to get to here for you is basically we're going to take a look at a house that only has an HVAC and a zip load that is using a schedule. So this is something that we use quite a bit. So I want to kind of hit on this one really quick. So you can kind of get a feel for the way that we've put these together. So in this example, again, we've got tape module, residential module. We've turned off all the implicit end uses. We have the power flow module activated and the climate, of course. Our clock, again, we're running this for a week, this time in the winter time. We've created a schedule that is just a rough representation of a scaled power schedule that we'll kind of show you here in a second. Of course, these have different values for summer weekdays, summer weekends, and winter weekdays. Again, activated the climate module. Here again, we have this triplex meter. We have the house object, and we're going to look at the total load coming out of here. I've got this set for an hour, but let's do something more like 5-minute intervals. And then, of course, let's actually, I'm just going to get rid of the limit. If we get rid of the limit, then this will record basically until the end of the simulation. So we're going to look at this every 300 or every 5 minutes and look at the load shape that's produced by the HVAC system running and by this zip load model here. We'll bring this up. Again, we'll learn to type. Okay, it ran pretty quick. Then we can pull up the outputs on it. Again, it looks like our numbering has gotten off from the exercises, but it'll work for here. So you can see there's a lot going on this hot day, so it's kind of hard to see the actual zip load going on there. But then as we come over here, we can kind of see the shape, the way it's forming. What we really want to show is how we set that up. So, for example, here we set up our normal house system here, but in this zip load, we created a base power, and it took these values right here and multiplied them by 1. So that should give us a base load of effectively this load shape times kilowatts. So we should get a peak load somewhere in the neighborhood of 1.2 kilowatts, except for when the HVAC system is on, of course. And then we're going to drop back down to much lower values. Higher values. And of course, we've got things like the different zip fractions are assigned here. In this case, we've got a power fraction of 0.2, an impedance of 0.7, a current of 0.1, and then power factors for each of the different ones, and a heat fraction, or how much heat we're going to is this electrical energy converted to. So one of the things we can take a look at here is, of course, we can rerun this, and we can do something like make this power multiplier something more like 0.01, for example. We can really reduce that base load. So if we rerun that, and then open it back up, so you can see now when the HVAC system is not on, we're almost dropping back down to 0. So effectively what that zip load becomes is kind of it's the raw shape that you get underneath, and then the HVAC system gets superimposed on top of that. But this ends up being a way that we represent a lot of our models. By just doing an HVAC system, just doing a zip load, and then the other piece that we'll typically add in there, and what I'm going to do here is that heater is way too big for what I want to do here. So let's make this a much more reasonable efficiency. And then we're also going to add in a hot water heater now. I'm just going to cheat and grab one from over here. I'll go through this here in just a second. We'll just grab all the pieces. This model has hot water heaters set up in 2 different ways that you can use them. So the first is going to use what I call this water heater demand schedule. So it's basically just 0 or 1. It's basically, from until 5 a.m. it's no draw, and then for 10 minutes at 5 a.m. we're going to draw 1 gallon per minute. And then again at 6:30 to 6:35 we're going to draw another gallon per minute. And then we're also going to do what we call this state probability model, which is very similar to what I described, where we can use a load shape and feed that in to describe the probability of when an event might happen. So again, we have this house. We still have the zip load in there. We've now also added a water heater. That is a fairly typical water heater design, so a volume of 60 gallons, UA of 2, heating capacity 4.5 kilowatts. Some of these pretty standard things. Tank set point of 130 degrees. What we're now going to do is we're going to feed in the water demand as the state probability. The way we're going to do this is we've created a shape that we're calling a pulse shape that's using the state probability schedule. We've given it an energy, how much energy we want it to consume over a given amount of time, how many times we want it to activate, and how long we want it to activate each time. If you don't remember how these pulse schedules or pulse shape looks, go ahead and go back and look at the first module, and there's a better description about that, how that works. But effectively, that shape is going to get fed into the water demand so that we get a certain number of random water demand events from this water heater that is driven by the probability that I described up above. And of course, this is a water heater, so it has an impedance fraction of 1 and a power factor of 1, basically resist development. The second way that we can also do this is to just specify the water demand directly. So in this case, we just use the water heater demand schedule, fed it directly into water demand. Everything else is the same. And then we're going to use this multi-recorder. We're going to look at the two water heaters and compare their two outputs. Let me just run this guy again. Great, no errors. It's always embarrassing when I have errors in my models. And we will look at these two values, but specifically, okay, this highlights a good point. So you can see here, I actually captured the complex value of the water heater, so the direct power, which comes in as a complex number. Unfortunately, Excel has no clue what to do with these complex numbers. So there's another little thing we can do here inside of the GLM. We can actually say we just want the real portion. Which that was in there. This was added in there specifically to work with Excel. So we can now run it again. Open those two files up again. So now you can see we just got the real portion of these pieces rather than the entire complex value. Now what we can do is we can take a look at these. So we can see here, this is what is this recorder? We're doing this at 1 minute intervals. So we can see here that over the course of this, this is 24 hours, I think. Yeah. So this is the water heater load shapes over the course of 24 hours. So we can see the red, which is the shaped one, which is using the probability curve. We can see that because we told it to only come on with a probability of 1 during this period of time, it just came on. Whereas with the schedule-driven one, we were able to make it come on in these kind of little different pulses. And of course, if we modify either of these, we can make them look very much similar to each other. These are just kind of two different ways to represent the way that this can be pieced together. And then, of course, we can actually look at the total load in the house, which is now going to be a little bit crazy because we have 2 electric hot water heaters and a very big resistive heater and a zip load that's fairly large. So it's getting be a little bit nonsensical as a house right now. But you can see what ends up happening is the key point to why we do all of this the way we do, is that when you look at the load of a house, it's not a nice smooth shape. It's definitely not a single value. It's a series of pulse trains that as you move through the day, these pulse trains either elongate or tighten, depending on what is being driven, what loads are coming on inside the house. So you can see here, because I believe this is mostly driven by the air temperature on the HVAC system, we have a pulse train that's very close together. So we're consuming a lot of energy because it's hot outside, versus over here where we're seeing it's not very hot outside and the pulse train is elongated. So it's these kind of effects that we're really trying to capture by modeling these in this way. Now, when it's all said and done, if we want to look at what a single house might look like that we would typically put together, let's go ahead and we will get rid of one of these hot water heaters because we really don't need those anymore. Here we're going to actually go up to move this up to the meter. Measured real power. So we're just going to look at the power output of this house. We're going to make these things a little bit more reasonable. Some of these are kind of set oddly just to kind of show off some things. So we'll get these a little bit more lined up with what we really use them as. So we're kind of basically we're just initializing this close to the cooling set point so that we start in steady state. So now we just have basically kind of an average run-of-the-mill house. We're recording the power at the meter. We have this zip load that will do something on the order of, we're going to get about a 1.5 kilowatts of other loads on peak. If you look at the schedule up here, at the lowest, it's going to be something on the order of about 630 watts being consumed by every other load. Every other load in this case being not the HVAC and not the hot water heater. And then we're going to have this hot water heater that we're going to go ahead and use this state probability model that we've done. But of course, we're going to modify this a little bit because this is a little bit of a silly model at this point. So basically, we're going to say during this morning period, we're going to have a very high probability of having hot water usage. During these other periods, we're going to have less, except for at 1800 hours. Then we're going to have another high probability of a hot water event happening. And again, this is just kind of a made-up one to kind of highlight what's going on here. And so we can effectively see if I got all this right. Okay, great. So now we've just created a house that is running with a zip load and a hot water heater and, of course, the HVAC. And we want to see what the output looks like. Take a look at the measured real power at the meter. I think I did this on 5-minute intervals. So we end up getting something that looks kind of like this. So it ends up being, you can kind of see the overall pattern of when the HVAC is on and off, and you can kind of see the overall, when the HVAC is on or off, you can see kind of the base load shape. That's the representation. And you can kind of, when you're looking through here, you can kind of see tell what different things are coming on. So for example, this jump from 630 to 3800, about 3.1 kilowatts, that's probably the HVAC system coming on. Whereas here you can see this jump to 8,000, that's probably the HVAC and the hot water heater coming on at the exact same time. So we're getting some kind of big loads on there, which is why it looks so big. I don't think I have this model here, but what you can end up doing is, while this one single house looks a little odd, in fact, it is a little bit odd because of the way I put the settings in there. As you start creating, tens or hundreds or thousands of these models, you end up getting, and you diversify them correctly, you end up getting a load shape that is much more familiar to most people, which is the idea that you kind of get this diurnal load shape that is due to the diversity of all the different loads within there. So, for example, if we go ahead and grab this IEEE 13-node model, which is, I think this is just the GLM at this point. Yeah. So what we've created here, and this is kind of a good thing for folks to play with if you have MATLAB. So we've created a MATLAB script that basically will take this IEEE 13-node model and will replace all the static loads with house loads and give them some reasonable values and reasonable diversity so that we can actually use it to create a model that is, I guess, believable at this point, but also gives you a lot of indication of how we do it and kind of a walkthrough scenario of how we put these models together. We have some much more complicated scripts that are very similar to this one, but this one works specifically with the 13-node model and allows us to do things like add certain technologies to the 13-node system, like batteries or markets or things like that. Specifically right now I'm going to turn everything off except for the houses themselves. And basically you can see things like we're going to, what's the average house kilowatts that we want to generate? Do I want to have water heaters on there? What percentage of heat pumps versus gas versus resistance are on there? And this is kind of our way of generating a very large model in a very easy-to-use manner, because as you can probably guess, there's a lot of these things in here would take us a lot of time to just sit down and create say 1,000 houses. You see, just creating that one house was 100 lines of text. You obviously don't want to create that 1,000 times. So a lot of what we've done is kind of put this into a scripting language. So which I happen to use MATLAB because that's what I'm comfortable with. But it allows you to script it and kind of create a model that's diversified, can be based off of a power flow model, but you don't have to sit there and type it, in a million lines of model code. So basically, I just ran this really quick, and what we end up getting is this output model that's called IEEE 13 house.glm. And you can see in here when we do we look for the object houses, you see there's just basically houses now created at triplex meters all throughout the system. In fact, if we count them, we can see there's 629 of them. But it's using the same format that we just talked about. So, for example, here was an object zip load where we just are representing some kind of base power. Some of the houses have hot water heaters depending on what percentage of penetration you wanted to use. You can see we started using things like schedule skews to represent the diversity and things like that. And now what we can do is we can actually take this model and run it. So I've got to grab these and all the schedules that go along with it. Again, I'm going to put this over into my release folder. And we're going to run this. And you're going to see it's going to be a little bit slow because now we do have thousands of houses on here. Excuse me, we have 600 and some odd houses. But we're going to go ahead and run it and kind of get an idea of what this looks like. Okay, so you see this error message came up. It's actually a warning. I think we talked about this last time, but there was some issues at one point where we could no longer use numbers as names. So there's a flag that allows you to turn that off. In this case, we've turned that off and said, no, go ahead and let us use numbers as names, and we'll just take the chance. I've never actually run into a problem with it, but we keep the warning in there just in case. It's kind of, our sanity check there just to make sure. So I think I just ran this for a day. I hope I did. If I didn't, then I'll break it here in a second. But okay, it finished. So we basically ran 24 hours on the 1st of August. And, this is with the profiler activated. So it gives us a little bit of extra information, like how many objects were in the model and what was my simulation speed. So for example, I can look at we went at 2,000 times real time basically. So for running that day, it just took a few minutes or a few seconds. You can even see who's taking the most time to do calculations. And of course, as expected, because we have 1,000 of them, or 670 of them, triplex meter, house and triplex line, water heater, and zip load, they end up taking a bulk of the time combined. But you can see that as an individual object, they're not that slow. But really what we want to look at here is kind of take a look at the total transformer output. I think this is the only output I grabbed from this model. Is we can just take a look at what is the power out of the substation transformer, or our representation of the substation transformer. So if we take a look at what we really want is power in real, power B in real, and power C in real. And we can plot these. And you can see now that once we've added enough diversity throughout the system, created all of these, and all these 600 some houses, all in the same way. So they all have, the basic gist, which is the HVAC system, the hot water heater, and the zip load. By pulling these all together and kind of using certain types of randomizations within that population, we can create something that people are much more familiar with, which is a daily load pattern load shape that has diversity throughout it. So this is what the whole end goal of trying to represent these appliance models in this way, and that's what we're trying to get to. It's kind of my point there. But really, I think the best way to kind of understand and use these appliance, specifically the HVAC model being the most, HVAC and the hot water heater model, is to kind of work through these exercises, try it out, get a little bit of understanding, and then ask questions, I think. So that really is kind of the bulk of all the prepared material I have. I'm perfectly happy to walk through some more examples if anyone has any questions, or just answer questions in general. Anyone? There we go. I see somebody typing. That's good. Yeah, this especially since obviously I don't know everyone's background here, but typically when I give this one to power engineers, there's a lot of rollback of eyes and like, oof, really, we're going to go into all this. Again, why there is a lot of complexity available if you want it, but for most of our studies, this house right here represents basically everything you need, because what it does is allows you to represent the two biggest loads, represent all the other loads as a zip load. So this captures most demand response, and it also captures, for the most part, it captures volt-var optimization and CVR studies too. So for example, I'll use CVR because a lot of people are interested in that right now. To make this into a good CVR model, basically the only things we need to add into this is basically it's motor model basic and motor efficiency good. Now at this point, this becomes a great, of course we have to do this for every single house in there that uses a heat pump or a central air fan or central air. This becomes a great model to do CVR. You can basically kind of capture the overall effects by just a non-thermostatic load in the zip loads. So basically this says, if I lower the voltage, then I'm going to lower my power, but I still get effectively the same amount of work out of it. So this is a lot of your things like your computers, your TVs, and those type of things. Whereas your water heater and your HVAC system are much more of a closed-loop system. So if you lower or increase the voltage, then you change the way they actually interact with the environment, and those effects are captured in there. And the only reason to add these pieces in there is because it turns out that with CVR, a lot of the value in CVR comes from the customer side of the meter, and a lot of that actually comes from the fact that motors are designed to operate at somewhere in between, typically 110 to 115 volts is the design parameter, but most utilities are operating in more like the 120 to 125 voltage. So you actually get a lot of efficiency by moving your voltage down into the motor's design voltage range. And this lets you kind of capture that effect by doing that. So any other questions, any specific examples folks want to talk about? So whether GridLAB-D could do some kind of economic evaluation. So that's a good question. We use it a lot to get us the information that we need to do an economic evaluation. So it's not designed to actually take in the economic values and do something with them, but it's a great way of coming out and saying, okay, well, if I were to implement this technology, what would my actual benefits be? And then that gets to feed back into your economic model to make a determination about what that value is. So the example I'll use is, again, I'll use CVR. So it's determining the economic value of volt-var optimization and what that might mean to somebody is completely dependent on which utility you go to, what regulator you're sitting under, what market you're in. But one thing that won't change is if I have a specific feeder with a specific load composition, the CVR value or even a number of values that might represent CVR are consistent. And so what you would use GridLAB for is to create that thing that would say, okay, if I use this control strategy, here would be my peak reduction, say 1%, and here would be my energy reduction, say 3%. And then you would take those values and be able to feed those back into an economic evaluation to kind of say, well, what is that worth to me? So while it won't directly produce the economic values for you, it'll give you a lot better information to feed into that economic model. Is that the kind of question you're asking there, or are you thinking more like economics in terms of market interactions? Right. Okay, perfect. So yeah, the only other caveat to that is what we'll get into in January, which is the markets. So we actually have built-in retail markets into one of the modules, and so that can be looked at as a way of trading resources, whether it's DG or demand response, in a real-time market. And so what you can do then is evaluate the impact on, say, like consumer bills. So you can run the simulation with a flat rate, and you can run the simulation with a time of use critical peak pricing, and then you can run it with the real-time price. And you can, from that, you can look at what the customer bill effects were. So, on an individual customer, how did you affect their bill? So say there's 1,000 customers on this feeder. What percentage of them did their bill go up? What percentage did they go down? And then overall from it, you can kind of look at it to say, okay, did I create a revenue neutral rate so that the utility is still collecting the same amount of revenue coming in or out, which is typically pretty important to regulators. So you can start to evaluate some of those questions. But for the most part, really what you're doing is using GridLAB to get the technical potential, and then using that technical potential to determine your economic value offline. there any other questions? Well, if anyone else is like Daryl here, and it takes a few days to digest and kind of work through what this means and what questions you may have. Like I said, I'm going to post this video online here shortly. So I think we've gotten our video server stood up, so we should have that out facing here this week, so anybody can download these pieces, go through these examples again. I just posted up the Module 3 work into the SourceForge account, so you're welcome to download that. Try any of the examples. Like I said, the best way is to kind of get a feel for it, just kind of try it out a few times, and as questions come up, feel free to use the forums or email me directly if you have some very specific questions. Other than that, I think I'm about finished, and we'll kind of wrap up for the day. I'm okay with ending a little early, especially as my voice is fading. All right, well, since there's no more questions, we'll go ahead and end for the day. And thank you, everybody for joining, and we'll see you next month. Everyone have a great holiday.